All right, recording is rolling. So it is Tuesday, November 8th. So I know I showed you guys that fancy 2-week plan yesterday, but already changed the plan because there's a hurricane bearing down on us. I want to make sure that I get in the lab before that thing hits. And so we're going to fit in the lab today, which I still have more notes to tell you guys about types of collisions and impulse, but you guys know enough now that you can do the collision cards lab. So get you guys set up with that. We're doing this today. Keeping an eye on may not be here tomorrow, and there's almost certainly not going to be here Thursday, but we're waiting for the word for that. Don't see anything in my email. All right, so also, if you turned in your quiz on time yesterday, then I did get those graded. Your grades are uploaded to Focus. Now, you guys in class, honors classes, I did get these printed. Now, we're not going to get to these till probably next week, and got a special plan for that. But right. But yeah, chapter 9, momentum problems. At least you have them printed and in your hands. That's just for my honors classes. In case I use this recording for conceptual too. Right. But because the lab's pretty much the same. All right. So the lab page, here's how we're doing this lab. This lab paper I do have printed out. It's double-sided. And we've got to walk you guys through it so you guys know exactly what you're looking at. But we're just going to do one per team. So got so many prints. We're going to do one per team. But before I show you guys the page, right, which is just a framework for how to think about this lab, I bring up these collision carts, and we're going to do this demo. Right, so we got to put this in front of the camera so it shows up on the video. We got a big old track. Right, this track is 227 meters long. You guys have used this track before for other labs too. Right? Hey guys, everybody look up here. Everybody full focus. Right, it's going to take about 5 minutes here. Do a full setup so you guys know exactly what's going on. Then you have the rest of the class to talk to each other and help each other out. Right. We got these collision carts. Now the collision carts have some built-in magnets, so they'll naturally bounce off each other. Watch this. Ba-boing, ba-boing. Oh, look at that. Does that look a lot like Newton's cradle type setup? Okay. Hey, do you think that collision would be perfectly what? Elastic? Perfectly elastic? Probably pretty close to that. Perfectly elastic, right? Right. No, it's a low friction track. Not exactly zero friction, but pretty close. Right? Give this thing a little push and it'll just go. Right? Just like that. Take a little push. Right. Just roll. Right. Very low friction. Right. Yeah, thank you. Right. No, it's not perfectly no friction. I do want to talk about that. But not right away. So hold on to that idea because we have to mend this a little bit. But if you turn these around, I've taped on magnets with pads with opposite poles. Guys, what does north and south do? They'll attract together, pull together, okay? Which could create a different type of collision. So here, let's check this out. Ooh, and would that be called what kind of collision? Inelastic, right? Inelastic. Okay. Now you might have to push these. This is a little technical thing, but you might have to push these magnets up a little bit so that there's nothing like rubbing against the field here. So try to reduce the friction. Now the empty card itself, I know is 500 grams. If we're doing momentum, you guys remember momentum is mass times velocity, right? Right. And with all these collisions, you're gonna have to keep track of the momentum, mass times velocity. So we got 500 grams for an empty cart. But you can stack more masses on it. Like this guy itself is 500 grams. Boom, nearly doubled the mass because the magnets are a little bit, right? So now let's check this out. Okay. Boom, like that. Or how about the other way? Boom. Ooh, oh yeah. Right, and it's running into stuff. What? Slow down. Little hooks getting stuck on stuff. All right. So you got two different kinds of collisions. Right. That one I just did is inelastic. And again, the first one I showed you guys that he's like bouncing off each other. It's probably pretty close to the elastic part of the spectrum. Right. Pretty close to that. Okay. Right. So how are you going to keep track of like masses and velocities? So the masses, there's a scale back here, a digital scale. You can use that. Right. Or if you like, you can just take 500 grams. Don't know exactly what these magnets are. They're a few grams. Right? You can add on more masses. So like 500 would be like 1,000 grams, something like that. Okay. Right, now, how about speeds? Because that's the other thing you do, right? To make momentum, mass times velocity. Okay. So this is the first semester I've had these speed gates. So I did redesign the table with these speed gates in mind. Now, different groups earlier today have used a little bit different procedures. Some groups have used the speed gates and said, oh yeah, they work. They work especially well if you take these glue sticks. They figured this out. So this is what my AP students figured out. Ajay Kelper told me this trick. Okay, take a glue stick, put it here, and then run this through. Let's see if it grabs the velocity. Whoops, that wasn't far enough. Go. 23. Ah, come on. I can find space. Let's run it instead. There you go. Got velocity, 0.49 meters per second. So it has the units attached to it. Okay. Now, if the speed gate isn't working for you, and a number of groups, it's like, I don't know, kind of cumbersome to work with, right? Can you guys calculate the velocity by doing some kind of distance divided by time? Right? And hey, look, there's like a built-in meter stick in this ramp. Well, it goes like 227 meters if you need the full length, right? And you guys got some stopwatches on your cell phones. Hey, could you guys do the rolling distance divided by the time, and then get an idea of like how fast it's going, right? Now, one of the complications with a lot like this is the fact that it's a collision lab. You need to keep track of momentum before and also after a collision, because that's what I'm gonna have you guys compare. It's like, is momentum really conserved? That's kind of the main question that you're after. Is momentum really conserved? If I add up the momentum before and after the collision, right? And if you have like an elastic collision like this, you're gonna have two individual masses, each with their own individual velocity, right? So you guys see how you need lots of teammates, maybe more than one speed gate, maybe several stopwatches, lots of eyeballs to kind of these. Okay, so it's gonna be like a huge team effort. You guys get that? Okay. All right. So let me set all of the demos aside. Right, and gonna break out that paper and walk you guys through the paper so you guys know exactly what's going on with that. All right, so you guys' lab page. Again, this is just one per team, but there's two sides to this page. One for just general collisions, and the other side specifically for inelastic. Right now, you guys remember what makes inelastic is they're going to stick together. Right, this magnets are stick together. Okay? Which means that there's like one combined mass after the fact. Okay? Actually, let's start on the side. Let's start with just perfectly inelastic. Okay? Now, the way I designed this table, I had one idea in mind, which is that you would get one cart in motion and one cart you would start from rest. So like the first couple columns say what's the mass in grams. If you want to change that to kilograms, that's okay. But have grams as quick, right? You guys know an empty cart is how many grams? Like 500, right? Okay, so empty cart's about 500 grams. Right? You can stack more lab weight onto that. Right. Then this column is the velocity of one cart. So you get it in motion. You can either use speed gate or do distance over time and calculate it. Right? So one way or the other. You get how many. Now I typed on this page centimeters per second. You can do that, or you can do meters per second. So if you want to change the unit, let's go. You scratch it out. Okay. Then next here. If you start the other one from rest, see it says start from rest. Wouldn't that give it 0 units of momentum? Because mass times velocity 0 would just be 0, right? Right. And then after they collide, so the total momentum pre-collision. Can you guys do mass times velocity of the one that's in motion that's providing all the momentum to the system? Isn't that true? Okay. All right. So this is all the momentum pre-collision. You guys see how this table is going to lead you to the momentum pre-collision? You guys see a really dark outline around each of these cells in this last column, right? Okay, so that would tell you the momentum like per trial. So this first row could be one trial, and the next row maybe you could change something, change one of the masses, right? Okay, do a different trial. Right, then post collision. Now, if it's perfectly inelastic, that means oh look, they're gonna stick together. They stick together. Can't you just add the masses together? Add the masses. Is that true? Right. And then there'll be some common final velocity. So this side's a little easier to work with because there's only one post collision velocity, just like the entire mass all moving together. Right. Again, you can either use a speed gate or you can calculate it distance per time, okay, which I have a little bit more I want to talk about, but hang tight on that. It's a technical detail I'm going to save for the end here, right, before I send you guys to lab. And then total momentum after collision. Can you guys do total mass, combined mass times velocity to get the total momentum, right? And if this conservation of momentum really works out, then these two cells should be pretty close to each other, shouldn't they? Right? Maybe not exactly the same, but a little bit of experimental error. Okay. Now I created here, I just take these boxes and copy paste them down here, so maybe it's not super necessary, but you're really comparing these two, right? Is that okay? Right. Okay. All right. Now let's look at the other side, which is a more general type of collision, maybe, possibly something that's more elastic, right? And I had the same initial startup. So you get one in motion. You record both masses. Here, here's focus here. Right. You got two individual masses. Get one rolling. Start one from rest. Right. So the one that is rolling is providing all the momentum in the system, exactly the same as the other one. Right. But post collision is going to play out a little bit differently, because if these carts are like boing bouncing off each other, then each cart will have its own individual velocity. So take the mass recorded in the first half of the table, multiply by this velocity, you get the post collision momentum. Same thing for this guy, post collision momentum. So that's two individual momentums, isn't it? Okay. It's a little bit of sort of a typo here. I should have put a dark box also around this column. So momentum units here, momentum units here. You guys see that? Right. So you got mass times velocity for this cart, mass times velocity for this cart. Can you add those together and get the combined momentum? Right. Which I put down here. So you can take these two cells and add them together and get the cell. Is that true? And you're comparing what's the pre-collision momentum to the post-collision momentum, right? Again, ideally it should be the same. You know, a little bit of experimental error. Is it really going to be? Well, you guys can find out. All right, is that right? Right. Any questions so far? Because I just told you guys the main points, but I want to add a few little details. Okay. Are you guys good with the main ideas of how this is working out? Okay. So add some details here. One thing that maybe should have included in this lab is to keep an eye on kinetic energy. You guys know kinetic energy is 1/2 mv squared. Now, which type of collision did I tell you guys yesterday where kinetic energy should be conserved? Is the one that we stick or the one that are bubbling, bouncing? Bouncy, yeah, bouncy, elastic. Yeah, elastic. That's like Newton's cradle, right? Where the energy, the kinetic energy should be conserved. So even though it's not a space on the table, that might be like an extra investigation you guys can do on your own. There's some extra space on the paper that you guys can write down. Maybe try one of these trials and like write, hey, what's the kinetic energy before and after, right? But if they collide and stick together, I can guarantee the kinetic energy is going to decrease. Okay, so try both ways. Try one of each trial. And the one where they're bouncy, I bet it should be pretty close. And the one where they stick together, I bet it's going to be a huge drop off. Right? You guys get that? All right. There's one more detail I want to make, but I'm going to put this in a separate video. Here you go. So stop this one.